Let's talk about continuous functions. First of all, we say that some function f of x is continuous at a point x equals c if the following three conditions are satisfied. First of all, f of x must be defined at x equals c, that is, the value f of c is defined. Then the limit of f of x as x approaches c must exist. That means that the behavior of the function to both sides of x equals c is so that the graph approaches the same height as x approaches c. And the third condition, the value of the limit should be exactly equal to the value of the function. So not only the graph approaches the same height from both sides of x equals c, but also the value of the function is exactly at the same height. We usually say that function f of x is continuous on an interval if the function is continuous at every point of the interval, and if any of the three conditions above are violated at a point, we say that the function is not continuous there, or more precisely, function has a discontinuity at x equals c. Okay, let's have a look on several graphs. This is a graph of a function continuous at x equals c. So we can see that the graph from both sides approaches the same height, and the value of the function at x equals c also is equal to that limit. So generally this is the graph of a continuous function, just goes right through the point. Now the following two graphs are graphs of the functions not continuous at a point. The graph on the left at x equals c, the function is not continuous because the function is not defined there. Likewise, on the right, the function is not continuous at point c because the function is not defined there as well. For the second example, we have the function on the left. It is defined at x equals c. It's equal to this value, but the limit as x approaches c doesn't exist, because the behavior of the graph from the left side is different from the behavior of the graph from the right side. It's not the case that the graph approaches the same height from both sides. Likewise, for the graph on the right, the function is defined at x equals c. It's equal to whatever the height of this point is, but the limit of the function as x approaches c doesn't exist. The graph approaches one place, well, it actually doesn't approach any real number from the left, and it doesn't approach any real number from the right. So the limit on the right function doesn't exist, and the limit for the left function doesn't exist as x approaches c. Now on to the third example. Here we have a couple of graphs where the function is defined at x equals c. The limit of the function as x approaches c exists, but those are not the same. So the value of the function is somewhere here above, but the limit will be somewhere here at this height. Likewise, for this function on the right, the limit will exist, but the height of the function is not equal to the value of the limit here. Now let's talk about some properties of continuous functions. If we know that f and g are continuous, then it is known that their sum or difference will be continuous, their product will be continuous, and their composition will be continuous as well. And then the quotient of f of x over g of x will be continuous at a point if the denominator is not zero, if g of c is not zero. Certain functions are guaranteed to be continuous on their entire domains. So one of those functions are polynomials. So any function any polynomial is guaranteed to be continuous on its domain. That's a polynomial. Rational functions are also continuous on their domains. Rational functions are the quotients of two polynomials. Roots are continuous on their domains. For example, h of x being square root of x minus 5 will be continuous on its domain. And then all the trigonometric functions are continuous on their domains. Trigonometric functions include sine x, cosine x, those are good functions. They are continuous on all real numbers. And then there is tangent x and secant x. Those are continuous on some intervals, and it's easier to write it that those are continuous for x not being equal to pi over 2 plus a multiple of pi. Likewise, cotangent x and cosecant x are continuous for all values of x not equal to a multiple of pi.